So without further ado, please join me in giving a warm welcome to Professor Amir Ahmadi.
Thank you. Can you hear me okay? I guess it's not, this is just for the video. So thank you, Navid, for the generous introduction, and Chuchu and both of you for having me here. As Navid said, I did my PhD here. Really some of the best years of my life were at MIT. Really special place for all the students here. No rush to leave. He only goes south from here. So I want to talk about the complexity of finding local minima and polynomial optimization. This is joint work with a very bright former PhD student of mine who's now at Yale, Jeffrey Zhang. If there is time, maybe 5-10 minutes at the end. Can I go until 1 hour? Yeah. Sure. Yeah. Then I want to tell you about the connection to something more recent on higher order Newton methods. So the motivation is easy to describe. So think of a non-convex landscape of the type in the picture. So you have multiple local minima and maybe some global minima. And the question I want to ask is, if global minima are hard to reach, can we at least find the local min efficiently? And maybe some of you have heard some practitioners of optimization make statements of the following type, that I have a non-convex problem and I have some sort of descent method, maybe some variant of gradient descent, and I don't know if they're finding, the method is finding a global min, it's probably getting stuck in a local min and returning a local min, and I want to examine that hypothesis. Is it really returning a local min, or how easy is it to find local minima? So let me formally give you the definition. So suppose you're minimizing a function f from Rn to R and over a feasible set omega, which is a subset of Rn. So a point x bar is a local min if it's first feasible and if there exists some positive radius, such that if you compare x bar to its feasible neighbors just over this radius, the objective value is better, or at least is no worse. So obviously it's a much weaker requirement than global optimality. So in this one-dimensional picture, for instance, I have these 3 local minima. And how easy or hard it is to find a local min, of course, depends on what f and omega are and how they're represented. So in this talk, I want to focus on the setting where the data to the optimization problem is given by polynomials. So f is a multivariate polynomial, and the feasible set is given by finitely many polynomial inequalities, the g sub i's, right? And I claim that this is a natural setting. For one thing, polynomials appear as exact models in various optimization problems, or they could be approximating more complicated models by Taylor expansion. And because local min is by definition is a local notion, and polynomials can approximate arbitrarily continuous functions with arbitrary accuracy, this is a natural function class for us to study this question. And moreover, because polynomials are finitely parameterized, I can study this question in the Turing model of computation. So I can take the input to be all the coefficients that appear in all my polynomials. I can take them to be rational numbers. I can count how many bits it takes to represent these rational numbers. And then I can ask, what's the running time of the fastest algorithm as a function of this this input to return a local min of this problem. So let's see what happens for different d's. So the simplest case is when the degree of all these polynomials is 1. So omega is a polyhedral set and the objective is linear. So that's of course linear programming. And we know that is a convex problem. So local and global minima are the same and can be found in polytime. This is classical. So already the next case is very interesting. So now if I keep omega polyhedral, so the g sub i's are affine, but f is quadratic. So this is called quadratic programming. It was known already in the 90s that global minima are hard to find. It's very simple to establish this. And the question I want to ask is, what about local minima? Is it any easier? And in fact, this question had appeared explicitly in a paper by Pardolos and Vavasis in 92. So if I read it, it's exactly saying what I just said. So what is the complexity of finding even a local minimizer for a non-convex quadratic program, assuming the feasible set is compact? So I tell you on the next slide why they have this assumption of compactness. But for some of you who may have seen related things, I want to distinguish between 2 related problems In fact, today I will be talking about both of them, what I call the recognition problem, what I call the search problem. So the recognition problem is I give you an optimization problem, f and omega, and I also give you a candidate point. And I ask you, is this point a local min, yes or no, right? And then the search problem, the input is just the optimization problem, f and omega. I don't give you any candidates. And I ask you, does the problem have a local min? And if the answer is yes, ideally I want you to return me one of its local minima, right? So the recognition problem for quadratic programs were they established by Murthy and Kabadi, and if you've seen matrix positivity, this is a one-line proof, so let me go over this. So matrix M is copositive if its quadratic form is non-negative on the non-negative orthant, and this is an NP-hard property to check, unlike the similar looking property of positive semi-definiteness. But suppose you take this as a given, then consider the problem of minimizing this quadratic form on the non-negative orthant. Now, if the matrix is copositive, well, the quadratic, and then you check, is 0 a local min, yes or no? Well, if the matrix is copositive, then the origin is a local min, in fact, is a global min, because the function vanishes at the origin and is non-negative everywhere. Okay? If the matrix is not copositive, well, that means that there is a vector x hat with non-negative entries where the quadratic form is negative. But I can then connect x hat to the origin, and by homogeneity, the function will be negative on this entire line segment, in particular arbitrarily close to the origin. So the origin is not a local min because there is a descent direction, right? So if you could answer this yes/no question, you could check copositivity. Now notice that this is different than the search problem, as they explain here, that this does not rule out the possibility that could be another algorithm that finds a different local min that is easy to verify. In particular, why does this reduction fail? Because the problem of interest to me is, given a quadratic program, does it have a local min, yes or no? And there is no longer an if and only if between copositivity. So for instance, this matrix is not copositive, but it has a local min. Even though 0, 0, the origin is not a local min, there is another point which is a local min, which is at 1, 0, right? So that's why this reduction breaks. So the second comment I want to make is about this compactness assumption. So essentially they make this assumption to ensure that there will be a local min, right? Because if I minimize a continuous function over a compact set, there will be a minimizer, so that's a global min, and in particular that's a local min. So what we're looking for is guaranteed to exist. So this is not a decision question, it's a search question. And moreover, if I want to return to you a local min, maybe you should first ask, how are you going to represent this local min? What if the local min has irrational entries? But it was known already in the 90s that this is not the case. So for quadratic programs, there is always a local min with rational entries if the input is rational and he has polynomial bit size. So what we want is really out there, and he has small bit size. The question is just to find it. So conceptually, it's a little bit similar to, let's say, the problem of finding a Nash equilibrium in a biomatrix game. So it's a search question. And here's the result with Jeff. So we showed that unless P equals MP, there cannot be any polytime algorithm that finds a local min. So in fact, it's a bit more negative. It says that it cannot even get within exponential distance to a local min. So there cannot be an algorithm that runs in polytime and returns a point which is within distance c to the n, so fix a c, let's say 2 or 100, of any local min of a quadratic function over a polytope. Okay. Any questions about the statement? Yeah.
How does c relate to the size of the polytope? Or are you normalizing the polytope?
Yeah, you will see. So essentially, yes. So this will depend on the size of the polytope, and you will see when I give the reduction why this is chosen. You can present a normalized version of this. I guess your question will be answered on the next slide. Okay, so I won't give you of course, a complete proof, but maybe some elements on outline of this proof. So like any other reduction, this is done like any other hardness proof is done by a reduction. This is from the stable set problem. So as a reminder, a stable set in a graph is a subset of the nodes that are pairwise non-adjacent. So in this graph, for instance, I have 5 red nodes that do not share any edges among them. So the size of the largest stable set denoted by alpha is at least 5. And you can believe me that there's no stable set of size 6, so alpha is exactly 5. And the decision question is given a graph G and an integer between 1 and n. Tell me if there is a stable set of size at least R. Okay? And this is a classic NP-complete problem. And here is the complete reduction. It fits on the bottom of my slide. So we say take this problem and construct this quadratic program. Right? So the only elements that we carry over from the stable set problem is the adjacency matrix A of the graph and this threshold integer R. Everything else is fixed. So I is the identity matrix. J is the matrix of all ones. And then the feasible set is basically the convex hull of the origin and the simplex. And so it's compact as required by Pardalos and Vavasis. And to Pablo's question, the relevant number is here. So this number, first of all, you can trust me that the ceiling of root n can be computed in polytime. And you may worry that I have c to the n here, whether this is a polytime reduction, but let's remember the number of bits we need to write down c to the n is n, because it's log of this number. And I already need n squared bits to write a. So this is indeed a polytime reduction. And so essentially, this is the largest number we can write in polytime, and that's why we'll put it here. You can also do like 2 to the poly n. If you change this and you normalize it, so for instance, if you have an n here, you get that you cannot get within root n distance of a local min. Okay, so why does this work? And this is just a rough idea. So the main claim, which I will not be proving, is that the following is true. So this program has the following property, that if the graph had no stable set of size R, so if all stable sets were of size smaller than R, then the origin is the only local min, which has to be the global min also, and is the only one. But if there is a stable set of size more than R, then there could be potentially multiple local minima, but they are all at this orange hyperplane. So they make the last inequality tight. Okay, so this is where the proof goes. But if you believe that claim, then the statement is established, because suppose there was an algorithm that ran in polytime and always returned the point within c to the n of a local min of an arbitrary quadratic program. Okay? Well, run your algorithm just on these quadratic programs. Okay? Now, the distance from the origin to this hyperplane is 3 times c to the n. Anything in blue is distance c to the n to the origin. Anything in orange is distance c to the n to the hyperplane. So if your algorithm has this property, after it finishes, it will never land in the white region. So it will either go in blue or orange. And then you can reverse engineer it and tell me if alpha was less than R or more than or equal to R. Okay. Does that make sense? Okay, so that's as much as I want to say about this. And but sort of an implication of this, which may be obvious to some of you, but is nice to keep in mind, is that so if you think of like a local method, let's say gradient descent, or just pick an arbitrary polytime algorithm. So maybe you do gradient descent with a fixed or diminishing step size, and if you leave the polytope, you project back to the polytope. So projection takes polytime, and let's say you run this algorithm for n to the 100 steps. So now I have a polytime algorithm. Will it find a local min? And the answer is that, out of all instances of quadratic programming that can be written with k bits, so there's 2 to the k such instances, your algorithm is going to not find a local min, and in fact not even land within exponential distance on a number that cannot be bounded by any polynomial in k. So the number of failure cases would be super polynomial. Okay? So the message being that we should not expect simple algorithms to find local minima, even on this arguably simple looking problems where the objective is quadratic and the constraints are linear. Okay, so if there is any hope of finding local min, then at least for polynomial optimization problems, this has to be in the unconstrained setting, because already like my constraints had degree 1. I cannot simplify them any further, right? So the only question left here is if I have an unconstrained problem, so if I have a polynomial of degree d, can I test if he has a local min? And if so, return 1. So it turns out that if the degree is 4 or larger, this cannot be done. And this statement is actually key to the proof of the previous theorem. So we first proved it for quartics, and then we massaged it to make this into a QP. So I'm not going to go over that. The degree 2 case is classical. If you want to find the local min of a quadratic function, you simply find the 0 of its gradient. So that's a system of linear equations. And if you check if the Hessian, which is a fixed matrix, is positive semi-definite. And if both tests pass, then your critical point is a local min. It's an if and only if, and this can be done in polytime. Okay, so that leaves out one case, which is the case of cubics, which turns out to be much more interesting. And let me give you like one geometric reason why cubics are more involved than quadratics. So consider this bivariate cubic, and I'm plotting here is level sets and the region where it's positive or negative, and of course it's 0 at the origin, right? And let's try to imagine if 0 is a local min or not. So if I start at 0 and if I move in any direction down, I'm going to immediately increase the function. If I move like in this direction, I'm also immediately going to increase the function because I'm going to first pass the positive region before I get to the negative region. So this means that there are no descent directions. So if I'm sitting at the origin and I look along any line, I see the function going up. So this may fool me into believing that 0 is a local min, but it is not a local min because there is a parabola of descent. So if I move not along lines, but along this parabola, I will immediately decrease the function, right? So we need to worry about ruling out descent parabola in addition to descent directions. And this doesn't happen for quadratics. So I claim that even the recognition question is not obvious here. So if I give you a cubic polynomial, meaning I give you the coefficients, and a rational vector, and I ask you, is this a local min? How would one test that? So it turns out that this can be done in polynomial time, and this is because of the following characterization. So a point z is a local min of a cubic polynomial if and only if 3 conditions hold. So the first 2, you recognize them from standard nonlinear programming. The gradient should vanish and the Hessian should be positive semi-definite. These are first and second order necessary conditions. But you need a third condition. And the condition is that for every vector in the null space of your Hessian at the candidate point, so pick your Hessian at the candidate point as a vector of a matrix of numbers. And if he has a null space, for any vector in his null space, a certain other vector should vanish. So this is the gradient of the top homogeneous component of P. So P is a cubic polynomial. It has terms of constant degree 1, degree 2, and degree 3. Just collect all the degree 3 terms, call it P3, take its gradient, and this vector should vanish if you plug in a vector on this null space. Okay? And I want to give you maybe some intuition about where this condition comes from. So I claim that the related condition, which is not the right condition, but it should be clear that this is a necessary condition for local optimality, that on this null space, the top homogeneous component itself should vanish, so not the gradient. And that's simply because if you take your candidate point x bar, this is where you're checking to see if it's a local min, and if you look in the direction d and just see what happens to this univariate restriction of this multivariate polynomial, because d is in the null space, the second order term would vanish, and this univariate function looks like either x cubed plus a constant or minus x cubed plus a constant. Right? So either if you go in the direction d or in the exact opposite direction, you will immediately decrease the function and you have a descent direction. Right? So this cannot happen, but this condition only rules out descent directions. We need to also rule out descent parabola, like we saw in that example. And it turns out that the gradient vanishing is a stronger condition. So you can sort of see this from Euler's identity for homogeneous function. If the gradient vanishes, the function vanishes, and this condition also turns out to rule out descent parabola. Okay. So why can this be checked in polytime, where the first and second order conditions are are obvious or standard. And to check this last condition, you want to check whether a certain class of polynomials vanish on a null space. So first you can compute a null space for this matrix, for example, by solving linear systems. You compute the basis for this null space, so let's call it V1 to Vk, if that's the dimension of the null space, right? And I want to see if this vector is vanishing on this null space. Well, anything in this null space, it can be written in this form. And I just take the gradient of the top homogeneous component. This is a homogeneous quadratic function, which is now a function of the alphas. And I want it to be identically 0 as a vector for all alpha. So this happens if and only if all the coefficients of all of these quadratics are equal to 0. And that's something we can simply check. Any questions about the recognition problem of local minima for cubics? OK, great. But OK, so that's a good first step, but that's not what I was after, right? I mean, ideally, I wanted to also find a local min and not just recognize if a candidate point is a local min, right? And before we do that, maybe we should ask a simpler question. Can we even find a critical point efficiently? So a point where the gradient vanishes, right? So why is that? Because at least when I teach nonlinear optimization and I want my undergrad students to find local minima, usually the recipe is set the gradient to 0, enumerate your critical points, then evaluate the Hessian. If the Hessian is PSD, then you start filtering these points more and you isolate your local minima. So it may seem like this is a prerequisite step, but in fact, deciding if a cubic polynomial has a critical point is not tractable, of course, unless P equals NP. But somewhat surprisingly, at least to us, it turns out that a local min of a cubic polynomial can be found by semi-definite programming. And these STPs it's not a hierarchy, it's just one STP whose size of the PSD blocks will be n by n, when n is the number of dimensions. And you need to solve linearly many. In fact, at worst case, you need to solve 2n of them, and they each have size n by n. So this shows that, at least for cubics, the right way to find local min is not to first find critical points. You need to bypass that and directly look for local minima. Okay. So I want to give you some idea of these things. And the first theorem, in fact, very easy to prove. So I thought maybe I'd give at least one complete proof in this talk. So why is it that for cubic polynomials it's hard to find critical points? Yes?
So you mean like the issue that this implies that the critical points of a cubic polynomial is also can be represented by the bounded rational numbers or something like that?
I don't need to establish that because I'm not claiming completeness. It's just hardness, right? Right, so the claim is that it is a decision question, but I'm not saying it's complete, so it's not in NP. But if you could answer it, P would be equal to NP.
You're just saying you can model it as an STP, but the solution...
No, are you asking about the top one or the bottom one?
No, the bottom.
Oh, the bottom one, yes. Okay, that's a great question. So, in fact, the complexity will be equivalent to STP. So if you're familiar with STP feasibility, right, in the Turing model, we don't know if it's formally in P. Even in NP, that's I think one of the main open questions about complexity of STP. So I'm saying this is exactly equivalent to STP. If you could show this is in P, STP would be in P, and vice versa. Yeah. I'll comment on that in a few slides. Yes, I'm careful to not say this is in P. Yeah. Sure. Okay, so why is it that for cubic? So if you thought, gradient descent finds a critical point, maybe you didn't, but if you did, let me show you why it doesn't. Okay. So take the Max-Scott problem, for instance. So given a graph, I want to assign a value -1 to some nodes and +1 to some nodes, such that the number of edges that go from one side to the other are maximized. So here's a cutoff value 8, and here's an optimal cutoff value 23. Right? You can very easily model this as a system of quadratic equations. When I have variables 1 per node that are asked to be -1, 1. And this is simply counting the number of edges going from one side to the other, because if these two numbers are the same sign, I get a 0. If they're the opposite sign, I get a 2. And I'm double counting the edges, so I need to normalize by 4. This is literally saying the system is feasible if and only if there's a cut of size k. Okay? So very simple, you design a cubic polynomial in 2n plus 1 variables, where you just multiply these constraints each one by a new variable. So the last one times y is 0, and each of these by yi. Okay. And look what happens if you take the gradient of this polynomial. If you take the gradients of this polynomial, because this was linear in y, the derivative with respect to y just gives you back the max-cut equations, right? And the derivative with respect to x is some expression here. So if the graph had a cut of size k, we'll plug in that x, and this will vanish, and plug in y equal to 0. And this is now a critical point of P. Okay. Conversely, if you had a critical point of P, so an x and a y, where this function, this vector vanishes, we'll just pick the x, and that's your cut. Okay. So, but as I argued before, this does not necessarily mean that you cannot find the local min. So why is it that we can do local min? So I think at the core of it, there is a nice geometric fact about cubic polynomials that is extremely easy to describe, which is this. So the set of local minima of any cubic polynomial is a convex set. So the set of local minima could be empty, could be one point, or could be many points, but is always a convex set. So I won't give you, okay, and of course this is very special to cubics. For quartics, already in dimension 1, this is not true, right, as this picture demonstrates. And here's some intuition. So let's look at this cubic polynomial in 2 variables. The set of its critical points is the union of these 2 red lines, which is not convex. And sort of that makes sense, is the solution set of some system of quadratic equations. But then if you look at the set where the Hessian is positive semi-definite, this is always a convex set, because P has degree 3. If I differentiate twice, the Hessian matrix is affine in X. So the set of X's where is PST is exactly a linear matrix inequality, right? But what is nice is that just like this picture, the intersection of this non-convex set with this convex set remains convex. So in this picture, that's just the top red line. So the local minima will be a subset of this top red line, and this example, they turn out to be all of it. So this is the set of local minima, the top red line, which is convex. And the proof uses the characterization that I presented before. So of course, just because the set is convex, it doesn't mean that testing membership to it is tractable, right? So you need some additional algebraic structure. So the first question you would probably ask is that, is this set always polyhedral, maybe with a tractable number of facets? And it's not. It's easy to give examples. It's a cubic polynomial in 4 variables whose I'm plotting the projection of a set of local minima to x1, x2. And because the projection is not polyhedral, the set upstairs could not have been polyhedral. Okay? So it's not polyhedral, but sort of the next best thing is true, and this is the main theorem. The set of local minima of any cubic polynomial is semi-definitely representable. So it can look like some of these. These are pictures that are probably stolen from Pablo. And in fact, it turns out the converse of this is true. And this converse is actually much easier to establish. So the interior of any semi-definite representable set is the projection of the set of local minima of some cubic polynomial. And this is a completely explicit result. So we explicitly write down, if you give me a semi-definite representable set, I can tell you what is the cubic polynomial. It has degree, it has number of variables maybe twice as number of variables as your STP. So what this second theorem implies is that if you have any algorithm for finding local minima of cubics, your algorithm is an STP solver. Right? So this goes in both directions. And roughly, and this is to your question, if you look at our paper, there is a correspondence between STP feasibility and this question of finding local minima of cubics. Questions? Okay. I think I'm actually going way too fast, so I may finish way before. Yeah.
One further question I have is like if you ask it, like people closer to, let's say, fear of computation, by computing a point, they want an algorithm that runs in time log 1 over epsilon.
Yeah.
If you ask a person closer to a mail, will say, I want poly 1 over epsilon.
Yeah, I would take polytime to mean log 1 over epsilon, because epsilon is the input, so log 1 over epsilon is the size.
Yeah, so I guess all the story you're telling us is about, all the inter-Hartman results basically are for very close approximations to the things, or even...
Are you talking about the critical points, or?
Like lots of inter-Hartman results we saw in this lecture.
Yeah, yeah.
About, critical points, local, local
Yeah.
minima.
Well, the local minima of quadratic programs was about not even getting close.
Yeah,
Right.
yeah.
So that's actually very far from an arbitrary small epsilon, right? The only other one we saw was about critical points. So the way I gave the proof, you're right that I'm asking that, can you find okay, so I'm asking the existence of whether there is a critical point or not without asking you to even return one. So this is a yes-no question, right? This is a decision problem, and I'm mapping it to whether there is a cut of this size or not, right? Now, does it rule out that you cannot get close to a critical point? This proof doesn't, but I believe it should not be because max cut jumps by integers, right? So you can probably do an approximate version of this, which says that if you get within some distance of a critical point, you could decide an approximate version of this.
I would
Yeah.
be surprised if getting close to an exact critical point or deciding, maybe it's kind of like, I guess in the end, the problem.
So you should certainly rule out, I think, getting within log 1 over epsilon. Whether it also rules out getting within poly 1 over epsilon, I don't know. But the QP one is much stronger than this, right?
Yeah.
Okay. All right. So I guess on my last slide on this topic, I wanted to give you maybe some intuition of where is semi-definite programming coming from? Like, why are this local minima of cubics, even if you believe it's a convex set, what's the connection to STP? And I just have one slide on intuition. And let's look at this univariate cubic polynomial, right? And of course, if you minimize it globally, we're going to get minus infinity. But what if I minimize it only over the region where the curvature is positive? So we call this the convexity region of a function, which is a set of points where the Hessian is PSD. And if I minimize the cubic over this region, at least in this picture, I get the local mean, right? And here's the formal theorem. So if you minimize over the convexity region, you get the closure of the local minima. And then we solve this problem. Now, the feasible set is an LMI, but the objective is not convex. It's an arbitrary cubic, right? So instead of solving this problem, we solve what you can think of as an algebraic dual problem. So the decision variable in the dual problem is not x, is a constant gamma, a polynomial sigma, which is the sum of squares. So let me remind you, a polynomial is the sum of squares if it can be written as a sum of squares of other polynomials. And a matrix polynomial S, which means a matrix with polynomial entries, which is an SOS matrix. So this means that this matrix can be factored as R transpose, where R varies polynomially with X. Okay. If you're friends with Pablo, you know that these two conditions have a semi-definite characterization. So and this equation on the right, on the top, needs to hold for all X. And I can impose that by matching coefficients. So that's simply a number of linear equality conditions on the coefficients of sigma and S and gamma. So this problem on the right is a semi-definite program in disguise. You can write it as an STP. Right? Now, why is it relevant to the first problem? Because we'll pick any primal feasible vector x. So the Hessian is PSD at x, right? And plug it into this identity. So the Hessian is PSD. S is an SOS matrix. So for any x is going to be PSD. And then the trace of the product of two PSD matrices is non-negative. And the sum of squares polynomial is non-negative for any x. So the right-hand side will be non-negative if x is primal feasible. That means that the objective will be more than gamma. So what I just argued is exactly weak duality between this problem and that problem. And in the paper, we also show strong duality already at the lowest level of this hierarchy. So when the degree of sigma and S is just 2. So these are polynomials or a polynomial matrix of degree 2. Right? So if you've seen the sum of squares hierarchy, this is sort of a matrix version of it, and we're showing exactness already at the first level. And that's where the connection to STP comes from. Okay. So I think I have more than enough time to to tell you a little bit about. Yeah. First time I think I finished early. So, all right. So this study of local minima, because of what you see on the next slide, motivated us to look at Newton methods, and this part is joint work also with Jeff and with the current PhD student Abrar at Princeton. So let me remind you all what is Newton's method. So if you want to minimize a function f, you start at an iterate xk, and you Taylor expand the function to second order. So you get this quadratic function q, and instead you minimize q. So that gives you the next iterate xk plus 1, and you repeat. More precisely, you move to a stationary point or a critical point of this second order Taylor approximation. And if f was convex at the point that you started with, this will also be the minimizer of this quadratic function. So what is the work per iteration? You need to find the critical point of a quadratic polynomial. So you set the gradient to 0. You need to solve a linear system. So let's say is like worst case n cubed, right? If you're a machine learning person, n cubed is really bad. But otherwise, I think Newton's method is amazing. So I'm not going to worry about that. I'm just going to worry about having polytime work per iteration. And perhaps the most well-known theorem about Newton is that while it may not globally converge, under some standard assumptions, it has local quadratic convergence. So once you're in a basin of attraction, the error in one iteration is smaller than the square of the error in the previous iteration. And you can see in this 1D example that this is very fast quadratic convergence. Okay? If you work with polynomials, it's very natural to ask, why did Newton Taylor expand just to degree 2? Like, it's kind of arbitrary. Why not Taylor expand to higher order to approximate f more accurately, right? And the reason, I guess, is obvious is because, how would we minimize in every step polynomials of higher degree, right? So I argue that even finding a local min is hard for degree 4 polynomials. Even finding a critical point is hard for degree 3 polynomials. But there was one thing that was easy to do with semi-definite programming, which is to find the local min of cubic polynomials. So this motivated Jeff and I to propose this third order Newton method, which is you Taylor expand to degree 3, and then you move to a local min by solving this semi-definite program, right? So this is hard to see, but here's a function f in blue. The dotted line is quadratic approximation, and the cubic, which you don't see, is this yellow line, which approximates the blue much better. And your next iterate would be here for the cubic, closer to the global min, and this is here for the Newton, right? Already we observed computationally that this method has sometimes better sensitivity to initial conditions. So if you've seen Newton fractals, these are a color coding of the basins of attractions of different local minima. So here's a function with 4 local minima, and every point gets one of 4 colors depending on which local minima is going to go to under the Newton map, right? And you can see as fractal structure. So there could be points arbitrarily close that move to different local minima. And this third order method seems to behave better. About a year after we proposed this, Jeff, with his own student, and I'm not involved in this work, proved the analogs of Newton's rate. So he showed that this method has local rate of degree 3, okay, which is nice. But then we asked, can we do higher degree? How do you go above degree 3? So this is the last thing I want to talk about, and this is the work with Abrar. And I'll be quite high level about it, so I'll describe the algorithm on one slide. So let's say you want to minimize the function f. What you do is first you start at an iterate xk, and you Taylor expand to degree d. This would be our dth degree Newton, for any d, but d is fixed. Okay? And let's call the Taylor expansion t d xk. And then we find the closest quote-unquote SOS convex polynomial of degree d plus 1 if d was odd, or d plus 2 if d is even. So don't worry about this, just sort of like 1 degree higher with the right parity. And if you don't know what's an SOS convex polynomial, all you need to know is that this is a subset of convex polynomials whose convexity has a certain algebraic proof based on sums of squares. So we find this closest SOS convex polynomial, and then we add it to sorry, and then let's call it psi, and then we minimize psi. And the next iterate will be the minimizer of psi. Okay, so what are the claims? The first claim is that steps 2 and 3 reduce to solving semi-definite programs of poly-size. So again, the work per iteration, at least to arbitrary accuracies, is polytime. And the other claim is that now that you have local convergence of degree d, right, which results in fewer calls to fewer function evaluations. So I guess I could give some intuition. So in dimension 1, these STPs are small enough that you can solve them by hand, or at least Abrar could solve them by hand. Maybe you can too, but probably I wouldn't be able to. So the degree 3 algorithm, just like this is the Newton map, this is the degree 3 algorithm. Maybe offline I can tell you a geometric intuition of what this is doing. But let me just end on an example. So this is comparing these two methods on this function f, which is this blue function and is strictly convex. There's a unique minimizer at the origin. And this is showing a trajectory starting from x0. The yellow is this method, which is minimizing a cubic Taylor expansion at x0, and then adding the smallest quartic amount to make it convex. And you see it's a very good approximation locally to this function, and that's compared to Newton. So the basin of attraction for Newton is anything between -1, 1, and this method is larger. And as you increase the degree of our method, so the basin gets larger. So yes?
Is that part of the theorem?
No.
Basic convergence will always be larger than standard Newton's method?
Yeah, so, okay, it's not because you sort of see that like Newton's basins can be fractal, like I showed you, right? So it's very improbable that there would be inclusion between a fractal and our set. So in fact, we have a 2D, I don't have a 1D example that goes the other way, but we have a 2D example where our basin is larger in volume, but incomparable to Newton. So there are points in one that are not in other.
And
yeah.
Do these higher order Newton methods rule out certain types of local minima? So for example, in the fractal picture, you were converging before local minima, but in the third order, there were 2 minima that you were converging to. So do you have a notion of what types of local minima?
Yeah, good. So the reason that's a great observation. So the reason you have 2 and you're ignoring the other 2 is because you could also think of a method where you tail expand to order 3 and then you move to a local max of the cubic, and that actually would get the other 2 local minimizers in this example. In general, we have no idea which local minimizer you go to. The only thing we can prove is that every local min has a basin around it, such that if you start there, you go to that one and you go with cubic rate or higher rate. Yeah. Okay. So just to end, maybe the main theme of this talk was really the first part on can we find local minima efficiently? And the answer is it really depends. So we should not always think that this is an easier task to do than find a global min. So already for some simple problems like QPs, you cannot get even close to local minima, but for some other problems, you may be able to get them, but it's not true that you can get them with any first order method, right? So in this case, for instance, we're getting them with semi-definite programming. I'm not sure if you could also get them with some, it would be interesting to see if you can also do it with, in polytime, with some version of gradient descent, say. So the first result is in this paper, the second one, this other one, and I'll stop here. Thank you. Pablo?
So do you have a sense of, I mean, it's not very practical, right, to solve an SCP and step.
Yeah.
But on the theory side, I mean, how does this compare to the cubic regularization stuff instead of...
Yeah, that's a good question. So the cubic regularization stuff of Nesterov, the initial paper, Nesterov-Polyak, is a bit different because the Taylor expansion is still of order 2, but they regularize it with degree 3, right? There's a much more recent paper of Nesterov called Implementable Tensor Methods, which he does the cubic case. So he Taylor expands to degree 3, he makes it convex with a similar idea, And he proposes an algorithm which takes polytime just for the cubic case, right? And I don't know if he's implemented it. We have never implemented this more than dimension 2. So I don't know which one is practically faster in the cubic case. But as far as I know, in the higher than 3 case, there was no proposal before. And the one thing about the cubic case of Nesterov is that the algorithm itself assumes knowledge of the Lipschitz constant of the function. So it's part of the, so you add to the tail expansion a Lipschitz constant plus some term. Whereas in this method, the amount we add is actually designed by solving an STP. It doesn't require the Lipschitz constant of f. So that's, so in degree 3, there are 2 competing methods. I don't know which one is faster. Yep.
So in the unconstrained polynomial case, do you know if any results on like having approximate critical points or local minima?
Yeah, so that's similar to the question that Kostis asked, right? Like any positive results, you mean? Yeah. I don't know. I mean, maybe Pablo would know. I don't know. So they're like for cubic polynomials. So for quadratics, of course, you can find it exactly. For cubics, how close you can get to critical points, I don't know. Yeah.
So,
Yeah.
So for higher than degree, I guess for degree 3, you only need local information to do your steps, or you need global?
Are you talking about the Newton method?
The third order division.
Yeah, so in the third order, I presented 2 different algorithms. So one is only works for degree 3, which is you tail expand to degree 3. So I guess for degree 3, there are 3 methods, including Nesterov. So for the degree 3, you tail expand to degree 3, and then you move to his local min by solving these STPs. The other method I presented works for any degree, in particular degree 3, but it does something different. You tail expand to degree 3, then you add something of higher order, 1 degree higher, and you add sort of the minimal amount to make this sum convex. In fact, SOS convex, so a little bit stronger. And the reason you add a higher order term, because near the iterate, you want the behavior to be governed by the tail expansion. You don't want to change the tail expansion locally that much, because that is what's giving you the local rate, right? So the second algorithm minimizes the sum of this regularization plus the cubic expansion by a different STP, not the STP I presented here.
Your STP, what information? I guess my question was around, do I need only local information?
Yeah, you just need a third order tail expansion, and the STP would add the 4th order term with a certain coefficient, which comes as an optimal solution of your first STP. Then that becomes fixed, and you minimize that convex polynomial of 1 higher degree with another STP. So that's why there were sort of 2 STPs in steps 2 and 3.
But to make sure that that thing is SOS convex,
Yeah, that's-
global information.
Sorry?
To make sure that that thing is SOS convex, you will need global information.
On F?
Yes.
No, so that's good. So I only need, the only assumption is that at the point that you're tail expanding, so we were trying to find the local min. So the local min, the Hessian just at that point is PSD, right? The only assumption we make is that instead of PSD, you're PD, right? Which is the same assumption for Newton's method to work. So you don't need global information because there's a lemma that any polynomial can be written as a difference of 2 convex polynomials. So for any cubic polynomial, as long as it has, okay, so if you give me an arbitrary cubic, I can add something to it to make it globally convex. And the term I need to add needs to have degree 2 terms and degree 4 terms. Because the degree 2 terms would dominate near the origin and take care of convexity near the origin. The degree 4 terms would take care of infinity, right? So here, we're only adding degree 4 terms because you don't need to add degree 2 because the Hessian is already positive definite. So yeah, no, there is no global assumption other than the Hessian being PD at your iterate. Yes?
In your slide, you have explained that the complexity of finding a local minimum of cubic is somewhat the same as solving a SDP stuff.
Mm-hmm.
So I'm just wondering if I have an arbitrary SDP, so is it possible to convert it to a solving a local optimum to solve a cubic?
Exactly. So that was the easier theorem of the two. I can tell you a little bit roughly about how you would do it. So remember I had this second theorem. So you're asking about this. So if your SDP is written, let's say, in standard dual form, so you have an LMI, you have n m by m matrices, A1 through AN, and you're looking for scalars x1 to xn that makes the linear combination positive semi-definite, right? So call that like A sub x is an affine matrix. So your cubic polynomial will simply be y transpose A of xy, so which is cubic, right? It's quadratic in y and linear in x, right? And then finding a local min is equivalent to finding a strictly feasible point for your SDP. Finding a second order point of this local min, so a point where the critical point is a critical point where the Hessian is PST, is the same as finding a feasible point to this SDP. Yeah, so this construction is very explicit. That's why I said it has twice as many variables. Or, yeah. Yes?
So I guess, what is the implication for all the people running gradient descent in practice? Like, what should they do differently knowing this?
Okay, without further work, they should not think that they're getting local minima or critical points. That's all, right? On their additional assumptions, they can, possibly, or they need to worry about, I mean, there are convergence proofs about like various versions of local min under certain assumptions, right? But there should be maybe more work on counting the number of iteration it takes and what would one need to do to initialize at the right point, right? And if these theorems, convergence results are under the assumptions, then what is the complexity of checking these assumptions, right? So all of these are not always formal for practitioners. So that's, yeah.
So is the idea that it would take you many iterations to converge to a stationary point that's a local minimum, or that you are going to get stuck at a stationary point that is not a local minimum? I think that's...
Okay, so let me, I don't know if I understand your question correctly, but this is related to this, that we cannot find critical points, but we can find local min, right? So the reason is that, so maybe you're thinking like, if you find the local min, that's already a critical point, so why can't I find critical points? So the reason is that what if you have a function where there is no local min, but there are still critical points, right? Then you cannot apply this, right? So usually if you have, so it is true that every local min is a critical point, but there's no complexity implications between them, right? If you have property A, which implies property B, you tell me A is in P or A is NPR, that I know nothing about complexity B, right? So that's...
So maybe in the interest of time, if there are other questions, maybe they could be taken offline. Let's thank Amir again.
Thank you.